Good morning, folks. So, today I have a lesson for you on measuring reaction rates. In chemical kinetics, it is very important to understand how fast a reaction is taking place. That is what we want to determine. And we cannot see what is actually happening inside the reaction at the molecular level. So, we have to look at physical parameters that are changing to determine how fast a reaction is taking place. And for that, we have to take the help of the change in specific characteristics. For example, in the first case over here, for measuring reaction rates, we are looking at monitoring of mass. If you are using this technique to measure the rate of a reaction, then the reactants have to be initially in the solid or aqueous form, and the product should have at least one gas being produced. So what will happen in this reaction is that the solid mass, which has a specific mass in the balance, will produce a gas, and the mass of the substance is going to reduce over time because a gas is going to be produced and released from the container. And we can measure that mass change by placing this reaction on a balance. Right? So when this reaction is taking place, we have the solution sitting on top of the balance, so we can see how much mass is changing over time. And that will give us the rate, because the rate is going to be equal to the change in mass over the change in time, which is written as rate is equal to delta m, which is change in mass, over delta t, lowercase t, for time. And so that is monitoring mass. So if you are planning to use monitoring mass for a reaction, you have to analyze the equation that is given to you and see if the initial solutions are all aqueous or solid, and the final solutions or the products have at least one gas being produced. Second technique you can use to measure rates of reaction is the change in pH. Right? So change in pH is the acidity of a substance. So the reactant has to be either acid or base. So for this technique to be used, you have to make sure you're looking at the reactants and determining if one of them is an acid or a base. And the product should have the neutralized acid or base. Okay? So if that is the case, then you can use a pH probe or pH meter to check the change in pH of the solution over time. Rate is going to be equal to the change in acidity over change in time, or the change in pH value over change in time, and that will give us or tell us how fast the reaction was taking place. Okay, so first one was monitoring mass. We were able to monitor the mass because there was a gas being produced. In pH, there was no gas being produced, it was the acid or base was being neutralized. Also, next one we have is conductivity. Conductivity, in this case, the reactant or product, there should be a change in quantity of dissolved ions. So when you're going from reactant to product, there has to be a change in the quantity or concentration of the dissolved ions in the solution, because dissolved ions conduct electricity. If the dissolved ions are increasing, then the solution will conduct electricity to a greater degree. And if the concentration of dissolved ions is decreasing, in other words, you're forming a precipitate, then the conductivity is going to decrease. So how do we measure this? We can check the change in conductivity using a conductivity meter. So we have a picture of a conductivity meter here, and we can check how much conductivity a solution has during the reaction at different time intervals. The rate is going to be equal to the change in conductivity over change in time, and written down change in conductivity delta conductivity over delta time. Next we have is pressure. This technique can be used again if your reactants and products are all gases. But there is a restriction here. If you have reactants and products both are gases, you could use pressure as long as the coefficients of the reactants are not equal to the coefficient or sum of the coefficients of the product. I have an example at the bottom for you. So In the first equation I have is 2a plus 3b forms 5c. If you analyze this, the 2 and 3, so 2 plus 3 is equal to 5. And on the right hand side also is 5. In other words, the number of molecules, number of gas particles in the solution haven't changed. And if that's the case, then there is no change in pressure because, again, recalling from grade 11, pressure is dependent on the number of particles, not the kind of or the specific gas molecules. Right? So if you have carbon dioxide plus oxygen plus nitrogen, or if you have all carbon dioxide, it does not matter. If you have the same number of particles combined, then the pressure is going to be the same, right? And so therefore 2 plus 3 is 5 on the left hand side. We have 5 particles on the left hand side and we have 5 particles on the right hand side. The pressure is not going to change, so pressure is not going to be a good technique for determining the rate of reaction for this reaction. So not for this one. On the second equation I have, second option we have is 2a plus 3b forms 4d. 2 plus 3 is equal to 5. And on the right hand side we have only 4 on the product side. In this case, what we can use, so check mark, we can use pressure as a technique to measure the rate of the reaction. Because what will happen is as the reaction progresses, the number of gas particles in the will be reduced. In other words, the pressure will decline over time. In the same way, if you were to have a bigger number of the coefficient on the right hand side overall, then the pressure would have increased as the reaction progressed. Right? So the device that is used to measure the pressure is either a pressure gauge, and I have a pressure gauge as shown on the right hand side, or a manometer. Okay, a manometer is that U-shaped tube where you have the gas trapped on one side and you can have the atmospheric pressure on the other side. If the solutions on the gas side is higher than the atmospheric pressure, you can determine what the pressure overall is by taking the atmospheric pressure and adding H to it. And if it is below, then you subtract H from it because it is lower than the atmospheric pressure. Okay, so it is in relation to the atmospheric pressure. Right, so that is how a manometer works. And again, to figure out the rate, we are looking at the change in pressure over change in time, which is delta P over delta T. And that will tell us how fast the reaction is taking place. For these kind of reactions in which all of them are gases, but the stoichiometric coefficients add up to different values on the reactants and the products side. The next one we have is absorbance. This can be used in a chemical reaction where the colors of the reactants and products are different. As you understand from previous grades, color is a pigment which basically absorbs a certain wavelength of light. So what we can do is we can determine how much of a specific wavelength is being absorbed by the substance. And as the absorbance changes, we know the reaction is progressing. So if you can figure out the rate of change of the absorbance, then we can figure out how fast the reaction was taking place. So this can be used, again, as I said, reactants and products have to have different colors. And to use this technique, the instrument you would need is a spectrometer, spectrophotometer, or a calorimeter. All of these devices will measure the absorbance at specific wavelengths. So what we are going to be measuring is the change in absorbance over the change in time, which is the same as saying rate is equal to delta absorbance over delta time. And once we know that, we will know how fast the reaction was taking place. The last one we have here is volume. Okay, so the volume. So in this case, the reactant is either solid, liquid, or an aqueous solution. And a product, at least again, one product has to be a gas. And what we need to do is measure the volume of the gas produced by the reaction. And if you can figure out how fast the gas is being produced, how fast the volume is changing with respect to time, we will know the rate of the reaction. So in this case, rate is going to be equal to the change in concentration over the change in time, which is delta V, uppercase V for volume, over delta T for time. And that will tell us how fast this reaction is taking place, right? So that's the 1, 2, 3, 4, 5, 6 techniques you have here that are shown to you. So there are, so again, 1, 2, 3, 4, 5, and 6 techniques for you. So that will help you to determine the rate of the reaction. You cannot use all techniques at all times. You have to analyze the reaction. You have to analyze the chemical equation, and based on the chemical equation, decide which technique could be used. Sometimes more than one possible, there's one possible technique that could be used, and that is okay, but not all techniques can be used in all times. For example, if I have a solution which is all aqueous and there is no gas being produced, I cannot use monitoring mass because the mass is not going to change, right? And same way, I might be not able to use going down the volume, because in a volume I have to have a gas being produced, so I cannot use those two techniques. Those two techniques are right away eliminated. So you have to then decide which technique out of the 6 could you use to figure out the rate of the reaction. I hope this lesson was useful. You are able to understand that rates of reactions can be measured using different techniques, and it is important to analyze the reaction to determine which technique will best suit us to figure out the rate of the reaction. Continue looking forward to new lessons coming up soon.